In this video, we're going to take a look at an introduction to exponential functions. So the standard form of exponential functions is y equals a times b, which is our base, to the power of x. And an exponential function, like the parent function, the most basic form of it looks like this graph, and then we write it as f of x, or y equals 2 to the power of x. So there's two types of exponential functions. There's growth and decay. So to look at the different types, we look mostly at our b value, our base. When our base is greater than 1, we say that it's growing, and it looks like it's rising from left to right on the graph. But when we have exponential decay, the base is going to be a value that's less than 1, and it looks like it's falling or getting smaller from left to right. So our formula can be spread out a bit. So notice we have the b is our base, but then in order to figure out the rate of growth or the rate of decay, we can write that out so that we have 1 plus the rate, which together forms our b value. So I'm going to write that in, but let me change my color. I'm going to write it with the green. Let's see. Okay, so let's rewrite it just underneath there so you can tell that like this is still your b. But when we need to figure out the rate, we want to think of it as the b value is 1 plus the rate when it's growth. So it's bigger than 1. This is when b is greater than 1. Then exponential decay occurs when the b value is less than 1. So when b is less than 1, we want to think of y equals a, and then our base is 1 minus the rate. So that b value would look like it's less than 1 for that reason. And then we have our variables a, which is our initial amount before any growth or decay occurred. R is the rate, which we have to divide the percentage by 100. And then x or t can represent time. So let's look at a few examples. Example 1 says, suppose your community has 4,512 students this year. The student population is growing at 2.5% each year. Write an equation to model the situation and determine the student population in 3 years. All right, so we're going to write out our numbers and do some highlighting. So let's highlight this number, 4,512 students. And it says this year. And by reading the problem, we can kind of figure out that that was the initial amount. And so notice that's our a value. So a is the initial amount, and that's going to be 4,512 students. The student population is growing, and they certainly won't always put that in another color, but in this case, for this example, it is. But you want to look for words like growing at a rate per year. So that's growth. So that's telling us that we have a growth formula that we're going to look at. And then the rate they gave us is 2.5%. So rate of growth, let's write that down, is 2.5%. But we need to write it as a decimal, so we got to divide it by 100. Because we always divide it by 100%, and that gives us 0.025 for our rate. Because our calculators just can't do percent, we've got to use a decimal. That's the main reason we have to convert that number. Then we're going to write an equation to model the situation and determine the student population in 3 years. All right, so let's fill everything in. We have our growth formula is y equals, and let's just refer back up here. Let me write it in green, actually. We're going to use this formula and fill everything in. So y equals a 1 plus r to the power of x, which is going to be time. So y equals the 4,512. 1 plus the rate, which we put as a decimal, is 0.025. And then we have time, which is 3 years. So we have everything we need. We just need to type all that into our calculator. So let me grab my calculator. And we're just going to type all that carefully like it looks into the calculator. So let's see. I've got 4,512 parentheses 1 plus 0.025 and then to the power of 3. And then you got to round that off and think of people. Like what would make sense in terms of people. So I get 4,000 858.9 people, or we can round up, which would make a little more sense and just say, if rounded to the nearest person, let me see, it would be 4,859 people after 3 years. Okay, so that's the answer to that one, and that was our equation that helped us find it. Let's look at another example. Example 2 says the population of a certain endangered species has decreased. So decreased is a key word that helps us to pick out decay. So it's decreasing at a rate of 2.4% per year. Suppose there were 60 of these animals in 1999. How many animals were left in 2005? So if it's decay, let's refer back to our formula up here. We need this formula for decay. So y equals a, and then 1 minus the rate to the power of x, which is our time. So let's write out y equals a, 1 minus the rate to the power of x, which is time. I mean, we know that because it decreased. So it's decay. The rate was 2.4% this time. So let's write out rate of decay was 2.4%. So we need to divide that by 100%. I'm going to get 0.024 for our rate. And it says, suppose there were 60 of these animals in 1999. So 60 sounds like our A value, the original amount of animals. And then it was in 1999. So we got to think, how many years passed between 1999 when this started getting looked at to 2005, the final year it was looked at. So that is 6 years. So then let's plug everything in. So y equals the initial amount, which was the 60, 1 minus the rate, which we put as a decimal, was 0.024, and then 6 years is how long it took. And let's type all that in. So 60 times 1 minus 0.024 to the power of 6. And we get 51.862. But it's animals, so again, you want to round up or down to the nearest animal. So if it's 0.8, it would make good sense to, let's say, round to the 52, since it was larger than 5 after the decimal. Okay, so about 52 animals were left. Now, let's look at a few more examples of just picking out the initial value, the B value, and the rate. So I'm going to move my calculator out of the way. So for example A, we have y equals 4, 1.84 to the x power. So I noticed that my B value is greater than 1. That's my B. A is my 4. Here, let me write this a little better. Remember our original form, our standard parent function, or our original exponential form, is y equals a times b to the x. So when I say b is greater than 1, it's that 1.84 number. So that means this is a growth function. A is my initial amount, so that is the 4. B is the 1.84, the base, which told me that that was growth. Then the rate is how much bigger than 1 it is, because this is growth. So I'm just going to write that part out. Let me grab another color. Let's see. The rate is, in this case, how much bigger than 1. So if I have 1.84, to figure that out, I just have to subtract 1. And then I get 0.84 left over. So my rate of growth is 0.84. And then if I want to write it as a percentage, I've got to go backwards and multiply it by 100 to put it back into percent. So 84% is the rate of growth, is what you want to think, because that's how much bigger than 1 it was in our formula. Let's look at another one. So y equals 10.76 to the x power. So think of our exponential form as y equals a times b to the power of x. So a is the initial amount, which is 10. B is the 0.76. So we see that number is less than 1, so that is decay because b was less than 1. But the b value is related to your rate because you want to think about how much less than 1 is it. How much is it less than 1? Is 0.76. So what you can do is do 1 minus 0.76 to figure that out. And that would give you 0.24. So your rate of decay is actually that number, the 0.24. Because that's how much less than 1 this was. And then 0.24 times 100 would give us back 24%. And a lot of times we see the rate written as a percentage. All right, let's look at C. So again, let's write out our exponential form. So y equals a times b to the x. We see that a is the initial value, which is 45. B is the 0.78, and that's less than 1. So that goes with decay. And then the rate is how much less than 1 that is. So do 1 minus the rate to figure out the difference between the two. And 1 minus 0.78 is 0.22. And then you just got to convert it back to a percent by multiplying by 100. And you get 22% is the rate of decay. Because that's how much less than 1.78 was. Now let's just look at one more good example. So in part D, we have y equals a times b to the x. That's our exponential form. So a is our initial value of 1,000. B is the 1.05, which is larger than 1. So that is growth. And then the rate is how much larger than 1 that is. So if we subtract 1, we get the difference between the two, which is 0.05. Then just multiply that back by 100 and we get 5% is the rate of growth because that's how much bigger than 1 this was, the b value. Okay, so that's enough examples for now of growth and decay and picking out some values. So we'll stop there.